Welcome to Visual Algebra Lecture 1.3, Group Presentations. In the first two videos, we learned about groups and Cayley graphs, which are really nice ways to visually understand them. In this lecture, we'll learn about group presentations, which is an algebraic notation that encodes pretty much all information about a Cayley graph. Well, except for how big it is, which doesn't seem like a big deal, but as we'll see, that's actually a harder question than it seems. Let's get started. Before I can tell you what a group presentation is, we have to understand Cayley graphs a little bit better. Previously, we've labeled the nodes of Cayley graphs with configurations, like of a rectangle, a triangle, or a couple of light switches, or things like that. If we want to focus on a graph's structure, we can leave the nodes unlabeled. We don't really need them. For example, consider the following two groups of size 4. The first one we will henceforth refer to as V4. We've seen this before, right? This is the symmetry group of the rectangle and also the two light switch group. And the second one we have not seen before, and we'll usually be referring to it as C4. The abstract group on the left is called the Klein 4 group. Sometimes it's denoted V4, after the German mathematician Felix Klein. You might also see it written K4 or just V as well. Let me now pose two questions, and I encourage you to pause this lecture for a few moments and think about these before moving on. First, are the two groups whose Cayley graphs are shown above isomorphic? And second, can you think of an object whose symmetry group is the group on the right? Now, as I've posed these, it's suggestive that the answer is no, these are indeed different groups. And that is correct. But let's think about how one would verify this. Remember, if you want to show that two groups are not isomorphic, find a property that one of them has and the other one does not. And this has to be a property of the group, not the Cayley graph. On the right, this group has an action that's represented by the blue arrow, action or element. And that has the property that when you do it twice, you don't get the identity. In other words, it is not its own inverse. So this action, you have to do it 4 times to get back to where you started. And this group does not have an element like that. And you can't just check the blue and the red paths. You have to check all of them. Of course, the identity element doesn't satisfy that, but you have to check this one as well. So blue, red, that is its own inverse. And I'm not going to answer this next question about can you think of an object. I think when we get to the next slide, you'll see the answer for yourself. Groups that can be generated by a single action are called cyclic. These describe shapes that have only rotational symmetries. The shape of a molecule of boric acid is shown below. It should be clear that there are 3 symmetries. The identity action, which we'll denote as 1, a 120-degree counterclockwise rotation, which we'll call R, and then a 240-degree counterclockwise rotation, which is R squared. And as before, this is the same, or we consider it the same, as a 120-degree clockwise rotation. Just like how this, the identity, is the same as a 360-degree rotation. Here is a Cayley graph of the symmetry group of this molecule. The boric acid molecule is chiral because a mirror reflection is not a symmetry. This is different from what we saw in the first lecture, the symmetry group of a triangle. Inorganic chemists use group theory to classify molecules and crystals by their symmetries. As an aside, I'll say that I've actually worked on some problems in crystallography in the last couple of years, and I've done a lot of reading of books and papers by crystallographers, and there's some pretty hardcore group theory involved, a lot more than I had previously known. I always knew that there was some, but I didn't realize how advanced it really was. The triangle symmetry group which we saw in the first lecture, generated by a reflection and a rotation, it contains this cyclic group, which we'll call C3, as a subset. We say that C3 is a subgroup of the triangle symmetry group. It is a subset that is also a group. This will be the topic of an entire section, chapter 3, where we explore subgroups in a lot more detail. But for now, I just want to show you an example and be able to use the terminology because it will come up before then. When drawing Cayley graphs, we have done one of two things with the nodes such far. We started by labeling nodes with configurations of an object, like a rectangle or a triangle. We've also, starting this lecture, left nodes unlabeled. There is a third choice, since every path in the Cayley graph represents an action or element in the group. So we can label the nodes with these actions. Here's one way to do this for the Klein 4 group, V4. Here's how we saw it in the first lecture, with the nodes labeled by configurations of an object. Here's how we saw it in the beginning of this lecture. We just left the nodes unlabeled, which emphasizes its structure. And over here, we picked a node, say this one, called it the home state, and labeled it with the identity. And then we can label the remaining nodes with the remaining actions. So this is H, this is V, and this is the 180 rotation, which we can write as R or just as VH. By the regularity property of Cayley graphs, every node looks like every other one that we discussed. It does not matter where we start or what path we take when labeling. So I called this one the identity. We could have used any of these things. And I wrote this as VH. We could have written this as HV, or even as R, like we did in the first lecture. Here are two canonical ways to label the nodes of the Cayley graph of the triangle symmetry group, starting from the version we saw in the first lecture, where the nodes are labeled by configurations. So if we call this the home state in both of them, we label that with the identity. And then here, we label the outer ring R and R squared, and then the inner ring, we follow the blue path to get F, and that makes this FR and this FR squared. Whereas over here, we label these outer three nodes as before, one R and R squared, and then from each of those, we follow the blue path to get F, RF, and R squared F. So notice the difference. This node here is FR squared, but it's over here it's RF. And this is FR and this is R squared F. We've seen this before. These are relations that are equal. And both of these things are perfectly valid labelings. In this class, we will typically prefer this one. And that's just because nodes that are close to each other, so this pair, and this pair, have the same power of R than over here. So here we have an R and an R squared, and R and R squared. And that's just my personal preference. I'm sure, even though there's not that many people that use Cayley graphs, but I'm sure a lot of people who do use this convention. Technically, these are all right Cayley graphs because we are reading from left to right. In other words, traversing around the graph corresponds to right multiplication. This node here is FR squared, reading from left to right. This node here is RF, reading from left to right. Some books read from right to left, like function composition. Some books mix and match depending on the group. Functions are typically done right to left. Things like the quaternions, which we'll see soon, is done left to right. It really doesn't work well to mix conventions if you're using Cayley graphs. It just makes things a lot harder. So you have to pick one, and I've picked left to right. Other books will pick right to left. So just be aware, it doesn't matter as long as you're consistent. Let's make a few remarks about this. First of all, as I said before, every path corresponds to an action. And if you want to compute a path for a product of actions or elements, say A, B, then you can start at node A, or equivalently start at the identity node and follow any path for A, and then follow any path corresponding to B. So for example, if I wanted to compute r squared times f r squared, I can do this in either of these. I can go to the node r squared, or equivalently start at the identity and do r squared, and then follow the path for f r squared, so f r squared. And I see that that is equal to f. And notice that's the same over here too. Start here, do r squared, f r squared, and I get f. So a Cayley graph really is like a group calculator. It allows us to compute these things quickly. And if we had the actual relations on hand, we could do this as well. But it's just easier to do it when you have a graph like this right in front of you. Before we get to group presentations, I want to show you one more group of size 8. And this is a symmetry group of a square. This is generated by a 90-degree counterclockwise rotation, which we'll denote by R, and a horizontal flip, that is across a vertical axis, that we'll denote by F. So we call this the square symmetry group. Very shortly, we'll be giving this another name, namely dihedral. But for now, let's just call it this. And let me pose the question. Do any of these three groups that we've seen of size 8 have the same structure? In other words, are they isomorphic? What I'm asking you is, well, can you find a property that one group, not the graph, but one group has that the others do not? And if you can't, that doesn't necessarily mean that they aren't isomorphic. That just means you haven't been able to verify it. That's why this is a tricky question. So I encourage you to think about this and pause the lecture before I give you the answer. But we talked about in the previous lecture how these two are different because every element or action here is its own inverse. If you do it twice, you get back to where you started. Not just green, green, red, red, blue, blue, but also from any node, blue, green, and blue, red, and red, green, and finally there's one more, which is if you do start anywhere and you do red, blue, green, you get back to where you started. So this has a property that neither of these two do, because over here, if you do blue, green, blue, green, you got to do that 4 times to get back to where you started. So these two are different. But what about this one? Is this isomorphic to either of these two? Well, without too much thought, you look at this and say, okay, here's a element or action of where you have to apply it 4 times to get back to where you started. So this group has a property that this one does not, but this one does. So what about that? And it turns out that these things are actually isomorphic. So if you take this group and you generate it instead of by a rotation and a reflection, but by 2 consecutive, and this is what I mean by consecutive reflections, and you call this one T, and this one, call this one S, then this is the Cayley graph that you'll get. And maybe this wasn't a surprise for you because we saw this with the triangle symmetry group. This had 3-fold symmetry, and this thing ended up being a hexagon. Okay, at last, we're getting to the definition, which is in the title of this lecture, group presentations. Thus far, we've described a group by its generators. And we've written it like this. G is equal to angle brackets R and F. That means G is generated by R and F. However, it doesn't tell us how R and F generate G. A group presentation for G is a description of the group as the following. G is equal to a list of generators subject to a list of relations. And we use angle brackets to go around this, and we put either a colon or a vertical bar to separate the generators or the relations. And think of that as meaning subject to. The key idea is that a presentation is just an algebraic way to encode a Cayley graph. But it doesn't necessarily tell us which Cayley graph. Let's do some examples of some presentations right now. Here are some groups that we've seen. The first one is the Klein-4 group, V4, and it's generated by V and H subject to V squared, red, red, being equal to H squared, blue, blue, being equal to the identity. And also VH, red, blue, equals HV, blue, red. You can think of these as vertical and horizontal reflections or just as abstract letters. I could have used A and B instead of V and H. Now, if I had given you this, it's not entirely clear, maybe, that this is enough information to reconstruct this graph and not maybe something bigger or something smaller. That's a hard question, so think about that. Think about how you might know why this is enough information going forward. Here's another group we've seen, the triangle symmetry group. This is generated by R and F. You think of it as a rotation and reflection, subject to the following. R cubed and F squared are both the identity. Yes, if you do red, red, red from anywhere, you get the identity. And if you do blue, blue, you get the identity as well. And also, RF equals FR squared. So that tells you how F and R are related if you swap the order. So you can swap the order of R and F, but you have to change the exponent of R to an R squared. And finally, this last group, the presentation, well, it's generated by S and T such that S squared and T squared are both the identity. So blue, blue, and green, green are 1. And also STS equals TST. So blue, green, blue equals green, blue, green. Now for all of these, there are other ways that we could have written this presentation. All right, for example, this relation right here, I could have written as ST squared equals, well, let's see. So blue, green equals green, blue. So ST squared equals TS. And for this group, I could have written this one as RF equals F R inverse. So if you do red, blue, that's the same as blue backwards red. Now, here's a fact that I found really surprising when I first learned about it a couple years ago. And I learned about it from one of you, one of my viewers who emailed me to say, hey, this relation, R cubed equals 1 in this presentation is actually redundant. In other words, it's implied by these other two relations. So let's derive that. Let's suppose that we have the presentation RF subject to F squared equals 1, this relation, and this relation, RF equals FR squared, and let's derive R cubed equals 1. So if we have RF equals FR squared, we can do anything we want to both sides as long as it's true. So let's multiply by F. So if we do that, we get F RF equals F squared R squared. And of course, F squared is 1, so we can just ignore that. And now let's square both sides. So if we square the left side, we get FRF squared. So that's FRF. And you square the right side, you get R to the 4th. And you see what's going to happen? How these F's cancel. F squared is the identity. So that means that we have FR squared F equals R to the 4th, which we know is, well, actually, I wanted to say R to the 4th is equal to R, but I would be using this relation, so I can't do that just yet. So FR squared equals R to the 4th. So now what? Well, now we can put parentheses right here, and I can use this relation to write FR squared equals RF. So let's move down here. And so that's RF times F equals R to the 4th. And that's R times F squared equals R to the 4th. So that's just R equals R to the 4th. And now if I multiply both sides by R inverse, I get the identity equals R cubed. And so by that, I mean multiple R inverse times R equals R inverse times R to the 4th. And that gives us this. So we get this relation from these two. Now, just because we can write this presentation with only 2 relations instead of 3 doesn't mean we shouldn't. Doesn't mean we should. It's just easier for anyone reading this to see that R cubed equals 1 than to actually do this derivation. And as we'll see, the question of what is a minimal set of relations is hard. And it's always good to err on the side of putting in more relations. If one of them is implied, that's okay. We just don't want to have one too few. Okay, so here's the typed version of that, but I think it's just more effective to do it for you live. But I want to mention that earlier I said that an alternate version of this relation is RF equals F R inverse. So RF equals F backwards R. However, if you take that presentation right here of the same group, and now if you remove R cubed equals 1, you no longer get the same group. This is no longer implied. If you remove this and you just have, you just don't have that anymore, now you actually get this infinite group. And it's not a proof, but let me try to appeal to your intuition. This group is generated by R, the red arrow, and F squared equals 1. And now RF equals F backwards R. There's nothing in here that suggests that there should be a 3 cycle. Right? Suppose we did this for the square symmetry group, etc. We would have the same thing here. Now, the only thing that suggests that there's this 3 cycle here is this relation R cubed equals 1 that I removed. It was kind of buried in here with this R to the 1st and R second here. But here, we don't have that. And once we remove R cubed equals 1, we get this infinite group. So we got to be careful with presentations. These can be trickier than we expect. And we'll actually see in a couple, actually I think in the next lecture on infinite symmetry groups, we will see an object whose symmetry group is this one down here. So stay tuned for that. In the meantime, let me ask you a question. What happens if I have a group generated by R and F, but I take away all of these relations. Generally, as I take away relations, the Cayley graph is going to get bigger. Does that make sense as to why? If it doesn't, then stick around and I'll try to convince you of that. So what is a group generated by two elements with no relations? What would that look like? What would the Cayley graph look like? Pause the video and think about that, because I'm about to show you. Okay, are you back? Here it is. This is called the free group on two generators. And I'm going to call them A and B instead of R and F. So A is the red arrow and B is the blue arrow. Now this fractal-like property of this Cayley graph isn't really there. It's so I can embed it into the plane. So every path corresponds to a different node. Well, not every path. If you do A and A inverse, you get back to the identity. But if you don't have consecutive inverses, if you don't do any A inverse or A inverse A, same with B, then you will get to a different node. This is like the most unraveled Cayley graph on two generators. It's like the most unwound one. It's like the biggest that it could be. And I'm saying that loosely because we just saw an infinite Cayley graph in the previous slide, but so the cardinality is the same, but this thing really should be like bigger in the sense of most unwound. Now, see, how much do I want to tell you about this? Okay, well, why not? There's an entire field of mathematics called geometric group theory. And well, based on what you know about groups so far, let me just say that you can think of it as people studying properties of groups by looking at their Cayley graphs and thinking of them as geometric objects. For this example, this object is hyperbolic in that it has negative curvature. I'm not going to say much about this, but imagine that you draw 6 triangles. I'll say a little bit. You can tile the plane with this. 6 triangles around a point. It's flat. If you do 5 triangles around a point, and then you can build a, so if you do this everywhere, then you're going to build a Platonic solid, like an icosahedron. It'll close back up. But if you try to put 7 equilateral triangles around a point, it can't lie flat. I don't know if you've seen this maybe in another video. It has negative curvature. This one will have positive curvature. This was rounded everywhere, and this one is flat. This is an example of a space that has negative curvature, and there's a whole bunch of groups whose Cayley graphs, typically infinite ones, or they have to be infinite, will have negative curvature. And in geometric group theory, people study groups by studying the geometry of Cayley graphs and other spaces on which they act. So this is just a taste of what is out there. And when I said that the free group on two generators is the biggest group on two generators, that can actually be formalized. And we will do that in Chapter 7 of this video series, which is on universal properties. Let me now try to take a stab at explaining what I meant when I said that the free group on two generators is, in some sense, the largest or the most unwound group on two generators. And I'll do that by showing you how, given an arbitrary group on two generators, namely this one that we're familiar with, the triangle symmetry group, how we can construct that from the Cayley graph of this free group. So here's a slightly different presentation than what you're used to, in that the last relation, RF equals 1, just says red, blue is a loop. That's equivalent to saying R squared F equals FR. You can see that visually, or you can just check that algebraically. If we write RF equals fr squared, and we multiply on the right by r, we get r fr equals fr cubed, which is 1, so that's just f. So now rf equals 1. So what I'm going to do is take this Cayley graph and I'll put the identity right here in the middle. And now this first relation, r cubed equals 1, means that any time that I follow 3 red paths, I get back to where I started. So if this is 1, then r, that node is also the identity. Similarly, if we go backwards, this node is the identity, because from here, the identity, 1 has r cubed, that should be the identity. Similarly, f squared equals 1 means anytime that I follow 2 blue paths, that's the identity. So if I go up 2, blue, that's 1. Down here, blue is 1. So this is r. If I go up by 2 blue paths, blue, that should be the same node. That should be r. And similarly, these two nodes have to be the same, and those are colored via r squared. So I'm coloring all the nodes in this graph based on the equivalence classes that are defined by these relations. If I do this, it's not a proof, but you can see that I get 6 distinct colors. So every element in here is equivalent to one of these 6 nodes. So what you're looking at here is what's called a quotient. It's a way to collapse this most unraveled Cayley graph into the Cayley graph of a group with just 6 nodes. And that's right here. We aren't going to see this formally until chapter 7. There is a way to express this with universal properties and a commutative diagram, but I think it's just helpful to see the intuition for it right now. Let me show you a simpler example. The free group on one generator is the largest or the most unraveled group with just one generator. And that, if you use a red arrow for that generator, is just going to be an infinite line. If you want to, you can write that as 1 r squared, r cubed, r to the minus 1, r to the minus 2, r to the minus 3, if you want to do things multiplicatively. But this is actually a familiar group, or this is a group that you don't realize you're familiar with, is just the regular integers if the operation is addition. So I will use the integers 0, 1, 2, etc. Now, the group Z12 you're also familiar with, even if you're not aware of it. Everybody is. Everybody who knows how to tell time, that is. That's just the integer modulo 12. And so if it's 7 o'clock and you want to say what time is it in 6 hours from now, you add 6 and you get 1 o'clock. We all know how to add integers modulo 12. So I claim that this group can be constructed from this one, Z12 from Z. This is the free group on one generator by collapsing the Cayley graph here, like how we did in the last example. So I want to declare that I want to say that this node here is going to be equivalent to, well, it's out of the picture, but wherever this node 12 is, where this node negative 12 is, and so forth. And similarly, 1 should be equivalent to node 13. So how can you formalize this? Well, it can be done with a map that's called a homomorphism. And homomorphisms are not going to come up until chapter 4, but let me just show this to you now, again, for the intuition. The idea is that you take this group and, well, one way to see it nicely is to wrap it in a circle like this. And the equivalence classes, the things that are colored the same, are grouped like this. And so we group them like this, and then we just collapse them into single nodes. This becomes 0 mod 12. These are 1 mod 12. These are 2 mod 12. These are 3 mod 12, etc. So this is basically this is the map that collapses, does that collapsing, and this is the relabeling that just takes this equivalence class and reduces it and attaches the label between 0 and 11. So again, formalizing this, so we're not going to see this idea of a quotient until chapter 3. Well, formalized until chapter 3. The idea of a homomorphism we won't see till chapter 4. And the idea of a free group we won't see until chapter 7. But again, I think it's helpful to get an introduction to this right now. Let's finish this lecture with a couple of words, no pun intended, about the word problem in group theory. And that is the following. Given a presentation of a group G, let's say by n generators, G1 up to Gn, subject to m relations, R1 up to Rm, which are the identity, is G equal to the trivial group? Seems like a pretty easy question, right? Let me just emphasize this part here about the relations. So we've written sometimes relations like R F equals F R squared, but anytime we have something like that, we can always move everything to the left-hand side and write that as a single thing equaling the identity. And we just saw that in this particular case. We wrote that as RF equals the identity. So we can always write a list of relations like this. So basically I'm saying, given a group presentation, does it represent the trivial group? Seems like an easy question, or at least a doable one. And as an exercise, here is a presentation, group generated by A and B subject to AB equals B squared A and BA equals A squared B. That's actually the trivial group. What this is saying pictorially is that anytime you have a Cayley graph on two generators and you have this motif everywhere, red blue equals blue equals blue blue red, that's this, and red blue equals blue red, that's this, then that has to collapse down to the trivial group. Now, I encourage you to try this by hand, play around with this, and what you should get is that A equals 1 and B equals 1. But it's not easy. You have to play around with it and try things out, and eventually you should get this. But if you don't get this, you may wonder, maybe this isn't the trivial group. But how do you know that you didn't just put things together the right way to get everything to cancel? Maybe you missed something. And that's why the word problem is hard. Here's an even harder problem, the isomorphism problem. Given two groups, G1 and G2, that are also given by presentations like this, are they isomorphic? Now, we don't know how to prove two groups are isomorphic. There are tools for that. But this is a harder problem than just saying, is one group equal to the identity? And it really boils down to the following. Given a group presentation that looks like a large group, maybe one that we know, how can we be absolutely sure that it somehow doesn't magically collapse down like this? There are presentations that look a lot like this that are infinite groups. This one is the trivial group. Now here's the kicker. The word problem for groups is unsolvable, even for finitely presented groups, which means groups that have finitely many generators and relations. Note that these need not be finite groups. In general, they aren't. The proof of this is beyond the scope of this course, but I do want to outline how it goes and also what results it influences and is related to as well. And it's surprising because I'll show you a few things from seemingly unrelated fields. Let's start with a problem from topology. This is the four-dimensional sphere problem. Given a four-dimensional surface, determine whether it is homeomorphic to the four-dimensional sphere. Now, homeomorphic means topologically equivalent, meaning it has the same shape without the notion of a geometry. And I'm going to explain this by giving you the analog of the problem in 2 dimensions. And as I do that, I'm going to discuss an invariant that every surface has, which is a group called the fundamental group of all looped paths. So a two-dimensional sphere is just the surface of a ball. You know what that looks like. And this is homeomorphic to any other surface that looks like this that doesn't have a hole in it. So this potato surface. But it's not homeomorphic to a surface with a hole, like a torus or a two-hole torus. Now, how do mathematicians know this? Or how do you formally prove this? Well, there's something called this fundamental group. And what that is that you pick a base point, doesn't matter which one, and you look at the set of all looped paths. That means paths that start and end at that base point. And if you do that in a sphere, every such loop is going to be equivalent to, well, you could shrink that loop until you get down to one that just starts and ends at that base point. That's the constant loop. And you can do this because there's no holes in the way. We say we can continually deform a loop down to the trivial loop. But you can't do that here in a torus. And the reason is because if you have a loop here, well then maybe, or if you have a point here, and maybe there's a loop that goes around this way, and there's a loop that goes around this way. And neither of these loops are, we say, contractible to a constant path. Now in the two-dimensional surface, if you take your base point, doesn't matter where, but say here, then you might have a loop that goes around this way. Maybe we call this A. We might have a loop that, we will have a loop that goes around this way. Maybe we call that B. But we'll also have a loop that goes around this way. Maybe that's C. And then a loop that goes this way as well. So the fundamental group, well, you can also do this in one dimension. The fundamental group of a circle is the integers, because every loop is just equivalent to how many times it winds around the circle. So we say that the fundamental group of the circle is just the integers. This is the free group on one generator that we saw earlier. Here, the fundamental group on the two-sphere is trivial. We just say it's a trivial group because every loop is contractible. Over here, the fundamental groups are larger. So let me just tell you what this one is. The fundamental group of the two torus is generated by A and B, where AB equals BA. And I'm not going to prove that. I'm just going to state this without proof, and then this is more complicated. But basically, the sphere is the only surface whose fundamental group is trivial. So what we're really asking here is, given a four-dimensional surface, can we determine whether or not its fundamental group is trivial? So picture the four-dimensional analog of this. Now, 4 dimensions is big enough that for any group G given by a presentation, we can build a surface whose fundamental group is G. That means that the four-dimensional sphere problem is unsolvable. And here's a summary of the proof. Suppose there exists a solution of the four-dimensional sphere problem, and let's let G be a group whose word problem we wish to solve. Then just build a surface whose fundamental group is G, and use our magical solution to the four-dimensional sphere problem to determine whether or not S is a four-sphere. And all loops on a sphere are trivial. If we can do that, then we have solved the word problem for G, which we know is impossible. I should say that the unsolvability of the word problem is due to the halting problem in computer science. And that was something that was discovered by Alan Turing, I think in the 1930s. He thought of, before we really had computers, that we might one day want to build a computer program that says, does a given computer program that we input halt or not? A certain computer program will either halt or loop forever, and it'd be really nice if we had a halt checker. Well, he proved that that was impossible. Basically, that if you had something like that, you can embed Russell's famous paradox about there's a man or the barber in a town shaves every man who doesn't shave himself. Who shaves the barber? So basically, there's this inherent paradox embedded in a hypothetical solution to the halting problem. So that is unsolvable. And the proof of the word problem basically reduces down to the halting problem. It says if we could solve the word problem, then we can solve the halting problem. And this is just taking it one step further, saying if we could solve the four-dimensional sphere problem, we could solve the word problem and thus the halting problem. So I think this is a really neat connection between these famous problems, unsolvable problems in computer science, in algebra, and in geometry and topology. So I hope you enjoyed that too. In this lecture, we saw a handful of groups that were infinite, and we will continue that into the next lecture, which is on infinite symmetry groups. We will look at the groups of objects that repeat in 1, 2, and 3 dimensions, which are called friezes, wallpapers, and crystals. It's a lot of fun, so stay with us.